Okay, we're going to apply our Taylor series to partial differential equations. So we've got our Taylor series approximations to a partial differential equation. And so we're going to start with what we would call a forward difference. Okay, and here's the x-axis. There's 0, there's 1. And so what we're going to do is break this up, so here's h, 2h, 3h, and so forth all the way here to n times h. So we'll make all these intervals. If we think of our function u, right, it's got values here and here and here. Okay, but now let's say u0, that's the initial u, and maybe at some time later, u1, we would also have values. And that's the thing, we're doing partial differential equations. So what we want to do is take u sub t, which is equal to alpha squared u sub xx, and we would like to use our Taylor approximations for this. Now, so for the forward difference, what we're going to do is we're going to say u sub t is equal to, for any given spot in here, okay, so for any given x, if I'm going to call this a forward difference, then, now remember this is in terms of t, so I would have u sub x, or actually t first, so t plus k. Okay, so in this direction, we'll use delta t is equal to k, and in the x direction, we'll use delta x is equal to h. So a forward difference, again, would be something like this: u sub t plus k minus u sub t over k. Okay, and u sub xx, well, that is, oops, forgot my x's here, so we've got an x. Okay, so that's our partial with respect to t. Now our second partial with respect to x, at time t, we would have u sub t and x minus h minus 2 u of t and x plus u of t and x plus h all over h squared. Now, so what happens then if I substitute these two things in here, I will get u of t plus k at x minus u of t at x divided by k is equal to alpha squared times u of t x minus h minus 2u of tx running out of room, plus u of t x plus h, all divided by h squared. So ran out of room there. But there's my finite difference approximation. Now, here's the thing, is remember, if I start at, say, t equals 0, okay, t equals 0, I know that value, and I know this value, and I know that value, and I know that value. Okay, I know exactly what those are. And so what this method does is I can solve for the next time step, t plus k. So if I want to look at t plus k, then for each value of x here, along here, I can set up this type of equation. And so what I have is u of t plus k x is equal to, well, I need to multiply both sides by k if I'm going to solve for that. And so I'll do that, and I'll get alpha squared times k over h squared, and then times u of t, not sub t, u of t x minus h minus 2 u of tx plus u of t x plus h, and we've got that, and then plus u of tx. Okay, so from there, I move that to the other side. Now, so I'm going to use a new sort of notation. I am going to use u sub k, comma, I, and that is going to be shorthand notation for u of just in general, a k. Maybe I'll use a j here because we used a k before. So oops, there we go. So this is u of j, whoops, t sub j. That's really what I want. Okay, having my troubles here. T sub j and x sub I. Okay, so if I use that sort of notation, then what I'm going to say here is that u sub j plus 1, comma, I is equal to, so I've got that term, is equal to alpha squared k over h squared times u sub j I minus 1 minus 2 u sub j I, and plus u sub j I plus 1 and then plus u sub j I. Okay, and again, at time j, so if I start out at time 0, t0, I know everything on this right-hand side. And so I can tell you that value at the next time step. And if I do this for every single value of I get a bunch of equations. Okay, so if we go back here and look here, so here's x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, and so forth. So if I do this now, at the endpoints, I don't really need to because I've got boundary conditions. But if I do this at each of these points, make one of these equations, I get a big system of equations that are all very similar. Okay, I get this big system of equations that are all very similar and quite easy to solve. Okay, in this case, right? Because I know everything on the right-hand side here, and so I can just explicitly tell you that value. Okay, now I'm not going to go into numerical examples by hand here, because mostly I want you to get the idea. Okay, now and actually, when all said and done, again, because if K and H are about the same size, actually what I would prefer to do back here, kind of at this step, is instead of multiplying both sides by K, what I'd rather do is multiply both sides by h squared over alpha squared. Now, so if I do that, this changes a little bit. It becomes h squared over alpha squared k u sub j plus 1 I is equal to, now notice I'll end up needing to multiply that by the h squared over alpha squared. So what I'll have is equals uj I minus 1, and then I'll get plus h squared over alpha squared minus 2 uj I, and then plus uj I plus 1. Okay, and again, I know everything over here on the right-hand side, and so I can evaluate that, and then I'll just divide by that again, but we'll see in a moment why I like this better. And we get our answer, and it's very quick and explicit. The problem is this is not a very stable method. And by that, what it means is I have to make sure h is particularly small in order to know that this will actually give me, will converge to my answer, will give me a decent answer. And so this is just not the best method. But this was, we call this the forward difference method. Again, conceptually and algebraically and so forth, this is a very easy method because I can solve explicitly for each term very quickly from each of these independent equations. Now, this can also be called the forward Euler method. Okay, so that's the forward method.